The helical wind turbine CFD analysis is a critical tool for designing efficient vertical axis wind turbines, especially for urban environments. Unlike traditional propeller-style turbines, helical designs can capture wind from any direction and operate with less noise. However, their aerodynamics are complex. Using ANSYS Fluent, engineers can simulate the unsteady flow around the twisted blades to accurately predict power output and identify areas for improvement. This report details a CFD simulation focused on understanding the torque generation and complex flow physics of a three-bladed helical VAWT CFD model. Hello to you all ANSYS users. Welcome to Helical Wind Turbine CFD Simulation. So up to now, we created the geometry model and then meshed it using Fluent meshing software. And it is time to delve into the solver settings. So I want to start by loading the latest version of ANSYS Fluent on my system by putting down Fluent in the toolbox of the Windows. And then we can follow the root button and locate the mesh file that you receive with the other files. As simply as that, we can start the launcher. But before that, notice it would be much better to activate double precision box in order to have higher accuracy because it will calculate all the variables up to 16 decimals. And then based on your system and configuration, you can employ higher number of processors. Regarding my case, I'm gonna employ 8 processors for this simulation. So, meanwhile, we can take a look at our major reference, that is the paper entitled Effect of Helix Angle on the Performance of Helical Vertical Axis Wind Turbine. So, this was a major reference, but this is not a validation study. So, we just take it for references for many of these parameters, and more importantly, it's about the physics of the model. So as you already know, in the geometry creation step, we had established 2 different regions. One is called a stationary region, which is this rectangle, but in 3-dimensional. And the other one is the rotating, which is the rotor of the turbine. So in total, we can say we have 2 distinct regions, and then we meshed it with a great, actually, accuracy around the interfaces of both regions and also around the blades. And as you can see in here, we need to have a very extended domain compared to the diameter of the rotor. As you can see, it is 30 times bigger in the downstream and 50 times actually in the upstream, and also from the other sides. So this is a major reference and we just need to mention it. So let's begin into ANSYS Fluent. Before start, I just want to display one more time all the boundaries that we have specified. So this is the total domain and you can see the coordination. But let me hide the outlet and also the symmetry boundaries that can help us better see what's going inside. So this is the inlet of the air, and these are our 3 helical blades and also the rotation axis in the middle. So let's just start by defining a new report. What I need in here is the force type of report, and it's about the torque or moment. So I want to call this torque. And from the report output type, you need to choose moment, which is the synonym of the torque. And as you can see, the rotation axis is about Z in the positive direction, so it's all correct. And our moment center is exactly in the middle. You can see the global reference. Let me just display it. This is exactly in the middle, and we cannot see that due to existence of this shape. So let me just keep the blades and the airfoils. And right now you can see the global axis, and this is our moment center. So I just want to calculate the torque over all of the blades and airfoils. It's a simple calculation. It's just this formula. You do not need any Excel for this. So this is a final tiny step size. You can see it's in order of 10 to the power minus 3. So let's put it in here. And I just want to let the solver to tackle at most 50 iterations in each time step to reach the convergence. And if I do it for 360 time step, it means that I'm simulating a full round. I mean, one round. All right, so I stopped the solution to actually check the results together, and I loaded the final case and data files I saved. So these are the results. You can see about 60,000 iterations were performed, and I manually stopped the solution. The point is that you can see in another tab the torque that we made report out of, but I didn't have access to the all data files. This is fine. I can have it just for limited time steps. But you can see the cyclic motion of the torque due to rotation of three blades. We're gonna have three actually peaks in our chart. I can also show that in the Excel file. I will show that. But let's just see how we can extract the animation file. So after doing the solution from the animation section, open playback, you would see all the animation sequences that we created prior to start the solution. And this is, for example, one of them. As I said, I don't have access to all the frames together right now, but I just did it for 8 time steps just to show you how to extract it. So after specifying, for example, this view, you can see the velocity streams and the velocity distribution around the turbine. And this gonna be my camera. After specifying and locating the camera, you can define the start and end frame. And also I want to keep this viewpoint, so I uncheck use a stored view because the stored view was very far away from this. And after all, change the write or record format to video file, and by pressing the right button, it will be written on the hard disk. So let's check the results right now. I want to start from the distribution of the velocity. You can see what is going on, exactly what we expected on the rotation and the transfer of the data between the stationary zone and rotating zone is happening due to existence of a sliding mesh technique and also introduction of mesh interfaces correctly. The point is that the separation is actually seen in here, and it's pretty obvious due to high angle of attack between the blade and also the incoming airflow at some specific rotational azimuth angles. The blade undergoes separation and dynamic stall. And this is actually the nature of the vertical axis wind turbines. And also in the downstream, we can see a vacuum which we see a decrease in velocity magnitude, but it could be different when it comes to pressure. We can clearly see the separation zone in here around the blade once again, and also this stagnation point regarding the low angle of attack of this blade compared to the incoming airflow. And this is where the flow is still attached to the blade, and we cannot see any separation at this point. So similarly, you can watch any specific variable that you're interested in, such as the kinetic energy, and all of this can help you to produce a great report out of your simulation. They will. The point is that when you save your case and run it, you can see the torque file without a format file, and you can just simply open it using Notepad. So in this, you would see the time step and also the torque that is generated at that specific time step. And by gathering all of this data together in a software such as Microsoft Excel, you can just plot it like this. And you can see that over a full round, I mean 360 degrees, we can see three peaks regarding three blades that we're using. And also in some areas, like the first half of this rotation, we can see that the negative torque is generated. And this is something that we need to think about in our next design, because this negative torques actually drastically and negatively affect the final power output of the wind turbine. So I hope you'll find this tutorial helpful. In case you've got any more questions, do not hesitate to ask us.